And there's no study set due today. There is 2 study sets next week, so there'll be one Tuesday and Thursday and the week after that. But we are starting on solutions. So these notes are for today and Tuesday. We'll probably go through 4 pages today. And yeah, and there's lots of great solutions cartoons. Like this is where chemistry gets to really do lots of fun. So we're going to do mostly math today because that's what a lot of solutions are. And this is actually a key lecture because if you get this, it is a little bit different. You'll see as we go through the units. And the first study set's kind of the basics, which we'll do. And then on Tuesday, can you guys hear my dog or no? All right, if she gets really annoying, we'll lock her up. She's trying to talk to the dog next door. So the key is with solutions is you have to label. So, you know, I'm always harping on that you have to label, label, label. And it is more particular than that because there are 2 parts to a solution. So a solution is made up of the solutes plus the solvent. And it's understanding and identifying which one is which to be able to solve for your parts. So the solute is being dissolved. That's why I'm dressed up as the rainbow squid because we're doing solutions. And so the solute is being dissolved. It is usually the smaller component. The solvent is doing the dissolving. Now, water is called the universal solvent. It is not actually a universal solvent, which is the problem of the big island of plastic in every ocean that we're figuring out how to clean up, which is actually really cool. Actually, something also very cool, more local, is the Columbia Slough, which is really disgusting and gross. They're actually doing a project where they're having people like adopt small, I can't remember what the correct word is, small sections of it and commit to cleaning it up, like planting certain plants that will clean it up and to go and pick up litter and stuff. Anyway, I met a woman who was going to do that, and I was like, blessings to her. She lives down that way. Water, if you are not told the solvent, it is water. Otherwise, so like here on question 2, it just says aqueous. If you see the word aqueous, that means water is the solvent. So water is the solvent would be like one of our assumptions. There's going to be other parts to the assumptions. Just looking ahead. No. Yeah, like this one, if water is not the solvent, I tell you what the solvent is, and you'll see that as we're doing problem solving. Normally, the solute is the minor component. So like here, this is only 6.9 grams of sodium bicarbonate, so that is the solute. And the major component is the solvent. So there's more water. There's 100 grams, so that is the solvent. However, and this is why we call water the universal solvent. If water is present, it is always given the solvent position, period. No matter what you read online or anywhere, if water is present. So where you run into that is alcohol. So alcohol and water mix beautifully, and you can have solutions in which you have more alcohol than water, but the alcohol is the solute, and the water, no matter what, gets to be the solvent. I had a student many years ago who argued with me, and I went and asked all 5 chemists on our campus and did not tell them that there was an argument or anything. I just asked them the question, and every single one of them didn't even hesitate to answer the question. Water is the solvent. And every chemistry book that I looked in says it that way. It's one of the beauties of Google that anybody can say anything they want on there. All right. So we're going to walk through with this example. Oh, here we go. Sodium. Oh, I don't have my board to write your names on. I'll write it on top of here. What's the formula for sodium bicarbonate?
Is it NaHCO3?
Ooh, look at that. the first one up on the board. All right. Yes, Major, it is. So bicarbonate, bi means hydrogen. So sodium bicarbonate, this is baking soda, and this is the solute solvent. So you always want to identify which one, the two parts. And these are the 4 units that we will mostly be using. And some of them you've heard of before, but I'm going to define them and then we'll solve. And we're going to only have 2 sig figs, so we are going to watch sig figs. So the M per M means mass, and so percentage is the grams of solute over grams of solution. Now, one of the things you want to be careful of is you really can't abbreviate, because if you abbreviate SOL, what the heck are you talking about? Even with solvent, if you abbreviate SOLV, you're not going to be able to read your handwriting. So you're going to want to write the whole thing out. What this means is the solution, it means our total mass. It's the solute plus the solvent. And then times 100. I usually don't say the times 100. I just move my place value. That's a personal preference if you want to write it in. So like with gas laws, you're going to always state the formula and then you'll do your math. So our solute is 6.9. And you do want to label fully. Everything's going to have 2 parts. So you can't just say grams. You have to tell me grams of what. And so you could say grams of solute, or if you know what the solute is. And then our total, which would be the 6.9 grams of the sodium bicarbonate plus the 100 grams. So it's not 6.9 over the 100 grams, it's over the total solute plus solvent. And then that's where I get 6.5. That's why it's not 6.9. That's probably the most missed piece on these, is students want the denominator to just be water, and it is not. It is the total of the two. All right. There is also, just as a side note on this one, there is also something called percent V per V, in case we run into that. Anybody got an idea what the V's would stand for?
Volume?
Yeah, and the thing that's interesting here is it's milliliters solute over milliliters. Actually, I guess it could be any unit as long as it's the same on top and bottom, over milliliters total, meaning of the solute plus the solvent times 100. So vinegar solution is volume per volume. So you'll often see that on there. Another really quick side note is you will still sometimes see, and you might see that happen on a study set, is we used to always say W per W, meaning weight per weight. But weight and mass are not the same thing because of gravity. So we do correctly, it's supposed to be M per M. There's also percentage M per V, which would be grams over milliliters. That is not density. And when we get into density, density is always the same unit. It would be grams of solute over milliliters of solute. So the second piece has to be the exact same thing. You can't have a mix of solute over solution and do a density. And we'll see that. We'll run into that, if not today, on next Tuesday. All right, mole fraction. Mole fraction is symbolized by an X. It's like a funky X. I just put it in italics is why. But it is obviously moles. So it's going to be moles per mole. But as I just said, you are not going to do anything as just mole and mole. We're going to label it. And the labels are just the same as the mass one. It's just now we're doing moles. So it's moles of solute over moles of solution. And there is no percent, so you do not multiply by 100. So it is always less than 1. Wow. Yeah. Because it's the fraction. the mole fraction, right? So that's why it's called a mole fraction. So for this one, it means we have to change our grams to moles. So we have our 6.9 grams of sodium bicarbonate. Now, I'm going to do it within the problem. You can always do it outside of the problem. Or actually, I'll have you guys do that for a moment. So if you don't have your periodic table, go grab your periodic table. You have to figure out your moles of sodium bicarbonate and your moles of water, and then bring the pieces together. And again, you can do it as a separate step and then bring them in. Just you have to label all your pieces, or you can do it in one setup where you change this as grams to moles. Again, labeling your pieces. All right, I'll give you a moment to do that or to find your periodic table. All right. Dog went in, so hopefully we won't have that disruption. Do you guys remember adding up sodium, hydrogen, carbon, 3 oxygens? You do that a lot. It's not, we're doing a little bit of factor label like we did back in Chem 221. We're gonna see some things from back in 221, but this is the big step. So when you add up your sodium, hydrogen, carbon, oxygen, you should get around 84 point something. I'm just gonna keep it as 2 sig figs, like 0.03 or something. And again, you can figure out how many moles that would be. And then on the bottom, you can do it again, or you can just label in your moles. That's our sodium bicarbonate. And then plus our 100 grams of H2O. And H2O is like 18.016 grams to 1 mole. So you have to add up the whole denominator, and so take the numerator divided by this total. And again, the answer is really small because there's a lot of water there. All right, moving on. So it's all about the units, and that's what today's lecture is, getting used to these units. All right, the last one we know is molarity. Molality is different, so be careful. And I wrote it with a little m because the unit is a little m. It's actually a cursive m, but it is a lowercase m. So I don't care how you've written your m's your whole life, for your sanity and mine, when you write a lowercase m, it has to be like Mount St. Helens. It doesn't have a peak. It's nice and little round hills. When you write a capital M, it would be like Mount Hood, where it's pointy. So molarity is capital M, molality is little m. All right, the units, they both start with mole for a reason, because it's chemistry, it's our favorite unit. And so they both, that's what they do have in common, is moles of the solute on top. And actually, here we go. Let's do molarity first here. What is the unit on the bottom for molarity on D? Molarity is moles per what? You're all thinking so hard. I can see the smoke. It was liters, but if you say liters now, it would be marked wrong because everything has to have 2 units. So liters of what? And this is the key. Well, the good news is it's the same as the percent
Solution.
and that it is liters of solution. It was always the total volume. It is why this is a question mark. We cannot solve it for this problem because we don't know the total volume. So we don't know the total volume. So we can't solve it. Or there is a way, we know the total mass, so we need the density of the solution. If we knew the density, the final density of the solution, we could solve it, which we have on the next one. So we're going to get to solve that. So that's why that one has a question mark. All right, molality we can solve, and molality is has a niche use. There's only one use that I know of, and we're going to get to it on the next page. And it's the lab that we used to do with this. And I'm not videotaping the lab because it's just me measuring temperatures. You would measure temperatures for 20 minutes of something freezing. And I didn't think you needed to watch me writing down temperatures for 20 minutes. All right, so it is moles of solute over kilograms of solvent. So I'm gonna put a little star because that one is different. It is just the solvent on the bottom. All the other ones are the solution in the denominator. This one is just the solvent. It's just how the math works out. And so somebody created this unit. So we would do our sodium bicarbonate, change it to moles. Again, if you already figured out your moles, you can just plug that number in. And then the water, we know it's 100 grams of just the H2O, and a kilogram is over divided by 1,000 grams. And that would give us the 0.82 molality. So we're going to do another question with that, but that's like on the next one. Capital M is molarity, little m is molality. So just kind of keep that in mind with these. And so on this one, we will be able to solve for molarity. And that is because I gave you density. Now, the wording is the key. These just take a little bit of practice to get used to how they're worded. And so again, the word aqueous tells us that water is the solvent. NH3 is our solute. And you're going to see this comment, state your assumption. This is not our full assumption. And so I'm going to help you with the assumption. If you have a percent, this is like when we did empirical formula. Your assumption when you have a percent, anybody want to tell me what our assumption is going to be?
It's going to add up to 100, so it'd be 28 grams of NH3, and then the remaining would be the rest.
Yeah, so 72 grams of water. So our total is 100 grams. So our solution is 100 grams. That assumption is if you have a percent. So if there's a percent. Now, with that, we're back to the same place we were up here. We know our two pieces. So what you can do, I'm going to have you can figure out your moles or you can set it up. I'm going to pause in a moment. The other thing I wanted, though, before I let you try it, is these are worded a little awkward. It tells us our commercial concentrated aqueous ammonia. This density is of the solution. This is why I'll be on Zoom when you do your next celebration or when you do your worksheets and stuff, to just make sure, and I do usually word it better than it is here. So that is the density of the solution. So we know our total mass of the solution, so we can find the total volume of the solution using the density. And so you're solving for molality and molarity. So I'm going to pause recording, give you a couple of minutes to try that, and you can take a 2-minute break. All right, if you're working on it, you can keep going. The answers are there, so you can check. And I was putting the answers on the study set, so you'll be able to check as you go along. All right, so for molality, state your formula. It doesn't matter which one you show first. So moles of the solute or moles of NH3 over total moles. I'm sorry, over kilograms of H2O. So you can state it how I did here, moles of solute over kilograms of solvent, or you can state it like that. It's kind of a personal preference. So the NH3, we have 28 grams, and NH3 is like 17.034 grams per mole. I do it all in one setup, but if you want, you can figure out what that number is. And then the water is 72 grams. Sorry, we want to label. Don't just say grams. Please put a label with it. So the NH3, same with our moles. And this is 72 grams of H2O, which 1,000 grams to 1 kilogram. And I only gave you 2 sig figs, so we end up with around 23. And you can just write little m. That confuses some students because they think of meters. So you can also write the unit as moles per kilogram. So either way, this is called a molal, is what the unit is called. All right, for molarity, we have moles of solute over liters of solution. So water is the solvent, not the solution. All right, so we'll have our moles, which again, you can put it in like I did here, where you do it in one setup. We'll just do it that way again. Or you can find it showing the work. I think it's really nice to show it as one setup. You're all capable of doing that, and it makes it just look a lot neater. And we have 100 grams total of the solution. Again, don't abbreviate because you'll confuse yourself. And then we know there's 0.90 grams to 1 milliliter. So we have to flip that. So 1 milliliter per 0.9, so the grams cancel. And we do want to be in liters. So a milliliter is 10 to negative 3 liters. And we would punch that in, and you should get around 15 capital M, or moles per liter. And again, label. Don't just say grams or milliliters. Make sure you have a label there. Questions? All right, so that's just the units. What we're going to see now is colligative properties. So my first year teaching, somebody needed me to cover for him because, I don't know, he had to go to the airport or something. This is 25 years ago. And he's like, yeah, I'm doing colligative properties. And I'm like, oh, okay, no problem. And I'm like sitting there thinking, what are colligative properties? And this is before, like, you know, we're all walking around with smartphones and stuff. So I had to go and look it up in a book. But I'm like, oh, just the vapor pressure stuff. So there are 4 properties. Oh, I wrote a note to myself just to remind you. You do have a lab due on Sunday. It does involve a little bit of kitchen chemistry. I was criticized last year by some students because the instructions are somewhat vague. There are instructions there, but it really does depend. I was actually really impressed because students were very ingenious on how they did the lab and how they experimented. So it is science, which is experimenting. So you're going, it's based on what you have in your house. There's also extra credit, and the deadline was supposed to be today. I put the deadline as today because you had nothing else due today, and also so you could kind of have your weekend off. But I will take the extra credit until Sunday, and then it's cut off at that point. Araceli, you submitted a video, and for some reason I can hear the video, but I can't see it. But you can email it to me. Sometimes Blackboard's just really weird. But also email me how many drops you had. So if you do the surface tension one, when you submit it, just write in the text box like how many paper clips or how many drops you had on the penny. So I don't have to sit there and count your drops as you're on the video, but that way I know who's the winner. All right.
Sorry, one question about the extra credit. When we do the number 4, do we send you the steps of it or just the picture?
Which
The one that we had at Google, I can't remember the name.
Is it the oobleck?
Yeah.
No, you can just send me the link and then pictures of you making it.
Okay. I just wanted to see if I have to like, record myself. But that's about it. Okay.
Oh, you can record yourself if you have a lot of fun. We made it like a month ago in my front yard. I went and bought, actually somebody went and bought for me 100 pounds of cornstarch, and I have a kid's pool. And so Damon's had to have made this because he has nephews. So if you have kids, but it's really fun. My class in the fall, a lot of them did this one, and it was really nice. In the fall, the weather wasn't as nice as it is right now. But yeah, you just go get a little box of cornstarch. The ratio of water to cornstarch is very vague, because it's a consistency, and you'll see. But it's called a non-Newtonian fluid because it doesn't behave. It's a solid and a liquid at the same time. So if you hit it hard, it is like the desk. It's hard as a rock. But if you just hold it, it oozes through your hands. It flows like a liquid. And has to do with the entanglement of its long polymers, super duper long polymers of starch, so thousands of units. And so it's like wet spaghetti that if you pick up wet spaghetti in your hand, it just is going to ooze through. But if you hit it really hard, it just makes a tangled mess and just like freezes in space. It's really cool. It's fun. The oobleck is still all over my yard. It's dried out, so there's just patches of cornstarch because we really haven't had much rain. But anyway, I consider it a mark of, like, this past Friday, half of the kids were sick, and so I only had 3 kids who were in my sunroom where I am now, and we just had a giggle fest. And it was like one of the greatest blessings. And I'm hopeful, like you guys, I also wanted to mention that I had a lot of fun reading people's 7 days of giggling or whatever. I think almost everybody picks 7 days of giggling as one of their things. And again, you can be doing that for like the whole month, 30 days of giggling. So just imagine. It was actually a real delight when you guys turned in your test, because most everybody had a smile on their face, which is really nice. You guys all figured out your celebrations were graded and posted yesterday. So, which might inspire you that you're like, yeah, I'll do extra credit. I don't know that there's another chance for extra credit. So do it. Get some free points. All right. And then go enjoy the sunshine. So colligative properties, there's 4 of them. So I'm just going to write them up here just so you have them there. VP, which is vapor pressure, not our vice president, whose name I can never remember, which is good because it doesn't matter. All right. Couldn't remember the last one's name either. BP, which is not blood pressure, it's boiling point. MP, which is melting point, and then OP. So these are the 4 colligative properties. And what they are is when you add solutes, the property changes. So the boiling point, when you add a solute to water, just for the universal solvent, right? When you add salt to water, the boiling point changes, the melting point changes, everything about it changes for these 4 properties. And so we're going to see why. So what vapor pressure is, we talked about it. Anybody want to say what vapor pressure is? Elegantly, maybe? Or you'll let me do it? So vapor is not quite the same as a gas, although it becomes a gas. So vapor is the gas above a liquid. So it was the liquid and it just evaporated. So the gas above a liquid, in this case, that would be the solvent. And in one word, what is pressure? And they all say in unison.
Collisions.
Collisions. Thank you, Max. It is the gas above the liquid colliding. So they're just colliding with each other. My simplistic way, that's what this picture is showing. So this picture here is pure solvent. It only has the blue balls, so that's supposed to be water. And so that it's escaping. So we're looking at how much escapes. So liquid has IMFs, a gas doesn't have IMFs, so how much has escaped? When you add the solute, what is happening is you increase the IMFs between solute and solvent. So if you have more IMFs, it's going to mean you decrease how much escapes because they're attracted to the solute. So they have attractions for each other, but they escape. As soon as you add something else, they're like, ooh, something new is here. And they have attractions for that. And so less escape, so you decrease the vapor pressure. So when you add solute, you decrease the vapor pressure. Sorry, that's supposed to say add, not T. That's the big picture. And the reason why is because you have greater attractions, less of it's escaping. All right. So the law is Raoult's law. I don't speak French, but say it however you want. There's the law. So my question here, what is it proportional to, is X of the solvent. And I have this question here because it's probably the most missed thing on like the worksheet and the next celebration. Because if you go back, something I did not mention, we did mole fraction here. I did it of the solute. You can also do the mole fraction of the solvent. And so X of the solvent is moles of the solvent over the total moles. So moles, instead of moles of the solute, we're looking at the solvent because the solvent is the one that escapes. If you look at this picture, the solute is not escaping. All right. The formula. Let's go back up and look at this formula. This P here, this is pure solvent. So that's why it says P of the solvent times the X of the solvent equals, this is usually considered the final pressure. And we'll talk about that as we do this down here. I write the formula different than you're going to find it anywhere online or in books because most students would get it wrong how it's written on other places. So, so we can write it as P of the solution or the final pressure. And you can write it as VP. Most people just write P is equal to X of our solvent. And in this case, that is the water. So X of the water times the pressure of the water. This is when the water was pure. So we just have to plug into the formula. What we have is 14 grams of solute of the ethylene glycol. That's our solute. And we have 10 grams of water. So water is our solvent. So back to the comment I made earlier, if it's anything else than water, the 14 grams is the larger one. That would be the solvent. But if water is present, water gets to be the solvent. It's just a rule because water is the essence of life for ourselves in this planet. And so it always gets to be the solvent if it's present. All right. The other piece of information is this 110 degrees. That is just the temperature. So vapor pressure changes with temperature. As you heat up water, obviously the vapor pressure is increasing. And so the boiling point of water is 100 degrees. So we're able to trick the water and get it even higher. So if we were at 100 degrees, the vapor pressure would be standard pressure, which would be 760. So we got even higher than the boiling point. So we got a really high pressure going here. This 1070 is going to be that P. We're going to solve for the total pressure at the end. So I'm going to pause and give you a moment to do your math. to refresh how to do things. And yeah, we can take a 2-minute. If you're solving, keep going. I'm going to go ahead and start plugging in. So we want to do moles of water. So we have 10 grams. You can also solve for each of your moles down here if you would prefer. Actually, I'll do that on this one. That you have 10 grams of water, you have 18.016 grams to 1 mole. So I actually figured it out. So 0.556 moles of H2O. If you're going to solve it outside, make it in a nice way that I could follow it. And the ethylene glycol, you add up. I gave you the formula there. And that is like around 62-ish grams per mole. So that comes out as, 0.226 moles of the ethylene glycol. All right. So if you want, you can solve down here. And then what we're going to do is the moles of the water is on top. And the total moles is in the bottom. Again, I actually solved it both ways. I set it up with doing it all in one setup. What I find is about half of you like to do it that way, kind of like what I was doing on these other ones where I just put everything in the setup. And then about half of you like to figure out your pieces and then plug the pieces into the puzzles. So this would be 0.556. Just make sure you label everything clearly that anyone can follow your work. So the person who has no clue what's going on, they would follow your work and say, oh, I see. You can write the formula, or you can just say EG or S glycol, and then that's going to be times the 1070 torr. Just leave it in torr. There's, for some reason, vapor pressures are usually done millimeters of mercury or torr. There's no need to change it. And our final answer, that's a coincidence, that comes out as 760. But that's what you'll end up with. Now, you are going to always be asked, we're going to see it on all these problems with colligative properties, does your answer make sense? So you're going to do the math, you crunch a number, you get a number, which is good news because it's math and you're just crunching numbers. You're going to state your formula, you're going to label everything. And does your answer make sense? Of course it does, because your teacher got the answer. You're going to have to tell me why it makes sense. And if it doesn't make sense, then you want to tell me why it doesn't. And it is that when we add the solutes, less escapes. So it holds on to the solvent. Meaning higher IMF, however you want to say it. So there's greater attractions, so less escapes. So less vapor escapes. Again, using your own words, I'm just trying to find words that work for all of you. So we see a decrease in vapor pressure. So the original vapor pressure was 1070, and our new vapor pressure with the solute is 760. So we saw a decrease in vapor pressure. So when I ask you to explain, I'm not wanting you to say, I added the solute, the vapor pressure went down. That's just stating what I already did. You're explaining to me why that happens. All right, the next piece is like a big picture thing. Without doing much math, it's saying which one's going to have the highest, which is going to have the lowest. Now, two things determine how much solute you have. So there's two pieces, is the concentration, and that little m is molality. So molality or molarity, concentration of the solute, and the number of solute particles. So solute parts. We're going to look at ions. So we're not going to write net ionic equations, but that was why we did it. Now, pure water, this is our starting point. This has no solute, so there's zero solute in this. That Is that one going to be the highest or lowest? Anybody? Have 50-50 chance.
Highest,
The highest.
It is the highest. Why?
because there's no additional solute. So
Yeah, you haven't held it in yet, and so we're back to the pure solvent. So this is, in case of vapor pressure, this is our highest vapor pressure. On the next page, we're going to do boiling point. I'm going to write the answers on there because when you go to study, like for the midterm, this would have our lowest boiling point. Boiling points are always an opposite thing, so it doesn't need as much energy to overcome the IMFs. We'll get to that on the next page. All right, so now we have to figure out which one has the most solute. And so we're going to create a unit that I use. I don't know if I made it up, but you want to take the concentration and you're going to multiply by the number of solutes, particles. And it was in a book that I taught with originally, and I don't know, I don't see these units, but I call them osmoles. So it's like going over the rainbow. I actually saw a rainbow this morning, even though there was no rain. There was like a cloud. It was a woman was taking a picture, and she said, "I'm not taking a picture of you. There's a rainbow." And I thought that was great. I wasn't wearing my rainbow hat, but I was like, there's other weird people out there like me. And then I was so excited to see this rainbow up in the sky right after the sunrise. And then there was this mom walking toward me with a little kid, and I like go up to her to tell her. And everybody's so afraid of other people because I didn't have a mask on. I was outdoors without a mask on. And so they're like, the woman's like huddling away from me, and the little girl's just like walking right straight up to me. I'm like, look at the rainbow. And she got all excited. Anyway, it's going to all be back to normal soon. So what happens here is if there's no ions, if it's covalent, you're just one part. It doesn't break apart. So it's not splitting into ions. And you'll see when we get to the next ones. So that means we have one osmol or osmolality. So the os just means, we're going to talk about osmosis in about a half hour. All right, sodium chloride, I'm pretty sure you all know, is NaCl. There's two parts to that. There's a sodium and a chloride. So we're going to multiply by the two ions or the two parts. And so 0.6 would be 1.2 osmolal. So each of the ions is 0.6 molal. So you have a 0.6, another 0.6. So even though it's a lower concentration, we actually have a greater concentration. Calcium chloride. So what's our formula for calcium chloride? Well,
CaCl2.
yeah, so just a reminder, make sure you have your periodic table. Calcium's a 2A, and so it's going to have two chlorines. So CaCl2, which means we have three ions. We have a calcium and two chlorides. So there are three ions. So you're going to see me do that, but I often write it as words because it's really good for you to review writing your formulas. So we have 0.5. So even though it looked like it was the lowest as far as concentration, it's actually the highest because there's three ions. So 1.5 osmoles. And again, I put the os in front, stands for osmosis, because that means we factored in the ions. So this is going to be the lowest vapor pressure because it has the most solute. And it's going to be the highest boiling point, which we're going to get to right now. Questions on this page, sorry. All right, let's move on. So boiling point, just like promised. So boiling point and freezing point are the same formula, and that's this beautiful formula up there. The delta T, what does that triangle mean? Triangle T,
Change.
change. So you remember that from last term. It's not triangle T. You don't want to be that person in physics saying, what does the triangle mean? You want to be that person going, and you don't want to be the person who's calling it triangle T, because then people are going to be like, I don't know if I want to be their lab partner, because there's a good chance you guys might get a B in lab in the fall. All right, so that's our change in temperature. It is a little T because we don't actually have to change the Kelvin, like in gas laws. K is a constant, and that is different for every compound. So the constant is depends on the solvent. And if you look down here, it's given for this problem, and you have a very different one for that problem. So here it's 4.68, and here it's 40. They range, there's a huge range. It is a different constant. This F is for freezing point. If it's for boiling point, it's given a B. They are not the same number. So everything has a K for boiling and a K for freezing. So it depends on the solvent. So you will be given it, or you're going to be solving for it. And then, of course, that M is what? Little M.
Molality.
Yeah, this is the moles per kilogram. This is what I mentioned. This is why we have this unit, is for these problems, freezing point and boiling point. And anywhere you went in this country and took this class, you would do this lab that it talks about down here. Except we're not going to do it, because it involves staring at a thermometer for 20 minutes and writing down temperatures. All right, so big point is these two questions up here. And so what happens to freezing point when you add solute? Well, the picture speaks, right, a million words or a billion words or something like that. That's a lot of words. Freezing point is a liquid becoming a solid, right? So melting point is a solid becoming a liquid. To become a solid, the big thing is a liquid is flowing, and a solid has a regular pattern, which is beautifully shown there in that picture. Now, if you add a solute, suddenly you have a big chunk of something here. It's not really that big, but when you add the solute, it interferes with the pattern. And that is going to lower the freezing point. This is why we salt roads when we get the super cold. Here we don't, because it messes up the salmon's habitat. But most places in the country, they used to put salt down on the road, and that lowers the freezing point. A lot of people will put it down on their sidewalk when we have really cold temperatures, so that their sidewalk doesn't ice up, and this is why. It's actually quite fascinating. They've gone beyond adding salt. So they, in Wisconsin, they put the leftovers from the cheese making. So whatever the stuff that's left after you make cheese curds, it's actually a really good treatment for the road, and the road doesn't freeze. When I was at my mom's, I have no idea what they're doing, but they treat the road like 24 hours before they get a snowstorm. So, right, we know when a bad weather's coming. So my mom's in New Jersey, and so they put this treatment down on the road, and I'm like, what are they doing? Well, the next day there's snow. She got like a foot of snow. I got to make a snow pig and a snow flamingo and something else. I don't even remember what. But the road, there was no snow. It's like, it doesn't freeze. And so it kind of worried me, because I'm like going, what kind of chemical compound? But then I remember people in Wisconsin telling me that in their state, they were using the leftovers, because it was actually like a waste. They had huge amount of cheese, like leftover waste. And it turns out it changed the temperature of freezing. If you go to Minnesota, where it gets really super cold, they have to put sand on the road. It doesn't change the freezing point. It's just giving them traction. But the temperatures get so low in like Montana and places like that they can't lower the freezing point enough. But the idea is if it gets colder and colder, it eventually kicks the solute out. But they manipulate and play. It's the same with at the airport. They treat the planes with something to change the freezing point. And I don't know what the solute is to do that. All right, for boiling point, it is like vapor pressure, that when you add the solute, you increase the IMFs. So the solvent doesn't want to escape. Solvent doesn't escape. So we had a lower vapor pressure, so that's going to give us a higher boiling point. You need more jiggles to escape. So you need more kinetic energy to overcome those higher, so more jiggles and giggles. So we have to give it a higher temperature so it gets rid of that attraction. So need more jiggles to escape. So they're holding hands really tight, and if we jiggle it enough, it does come apart. So freezing point, add solute. You decrease freezing point, you increase boiling point. This is that we mathematically can actually calculate how much it will change by depending on our solute and solvent. All right, so let's just go through the math. So this is a terpene. It's analgesic, anti-inflammatory. Oh, so topics. So that's because we used to do the molecule topic at the end of the term. You guys have already done your molecule topic. The next set of presentations are an innovation. And so, yeah, we'll see where you go with that. I did want to mention, because I can see Damon. Damon did a really, you all actually did really cool ones last term. Damon did his on biomimicry. And so I wanted to throw that out there for all of you, because there is this whole field of biomimicry in which, like the wind turbines, they actually have redesigned them so they look like the fin of a certain type of whale. And it gives it more aerodynamic and actually captures more wind. Anyway, there's some really cool stuff out there. So you could just pick one biomimicry. He did a couple, but that's a whole cool field. Or you get to write about plastic. So this weekend when you do your plastic lab, you also, part of the lab is you're going to talk about something innovative somebody's doing with plastic. So it could be cleaning up plastic. Some of you did that last term, and I'm aware of who did that, so you have to pick something different. But you could also, my other class did this last term, you could pick one specific company, and that's what a lot of them did, is they picked one specific company and what that company's doing. So I just bought miso. So miso is soy paste that I use in cooking, and actually the container was zero plastic waste or something, and anyway, it had a phone number on there. So there's all these companies that are doing that somehow, because it always comes, miso always comes in a plastic container, or there's a lot of groups that are doing stuff with cleaning up the plastic in the oceans or on the beach and stuff. And so you could pick just one specific company, or you could pick a project. Or you could pick a new type of plastic. So they are making biologically degradable plastics out of things other than oil. So it's just a page. So just find like what interests you. So there's like a new type of plastic being made out of eggshells, I think it is. And there's other ones too. I can't remember. All right. So that was a quick plug for that. Because it's the end of the 7th week. So our presentations are like in 2 weeks, or we'll talk about that next week. If we're gonna do them in the 9th week or the 10th week, I don't really care. The reason I have it for the 9th week, when I survey you, I will remind you of this. Memorial Day is the weekend between the 9th and the 10th week. And so I scheduled them before Memorial Day, assuming you would want to have them done. But that would be, it's in 2 weeks then. So we can discuss it. If you want to do them after Memorial Day, we can do that too. All right, so we're calculating the freezing points. We're going to state our formula, delta T, F equals KF times, you can write M or you can write moles of solute over kilograms of solvent. For many students, it actually makes more sense to write the formula like that. All right, so let's see, I'm going to actually solve for delta T, and then I will figure out what my change is. So this is, the normal freezing point is no solute present. So it's pure solvent, that's what it would freeze at negative 63. So delta T equals, the K is given to us. K's always have constants, have funky units, just go with it. Degrees Celsius divided by M. That's just so our units will cancel. And so there are two pieces given here. It tells us we have 42 grams of eucalyptol and we have 0.6 kilograms of CHCl3. So which one is the solute and which is the solvent? And how do you know? Because it's not water this time.
Is it the eucalyptol because it's bigger?
Eucalyptol is the solute because there's less of it. So it's not the size of the molecule. So my solute is the 42.0 grams of the, I'll just say euc. And then you would change your grams to moles. So this guy is the solute because there's only 42 grams of it. And then the 0.6 kilograms is my solvent. That's the CHCl3. All right, I'm pretty sure I already figured out. This is going to be around 154 grams per mole if you add up your 10 carbons, your 18 hydrogens. I don't actually care what the molality is. Some students will figure that out. I didn't. I just plugged this in and I get a number, which is not our final number. I get 2.13 degrees Celsius. Pause if there's questions. So I do this with logic because it works much better for all of us and it's good for your brain. I have really good logic skills. Rather than doing final minus initial, there's an issue that shows up. Every book that I've used and everywhere online does this different and it gets really confusing. So the KFs are sometimes given as a negative and sometimes they put a negative in the formula. I just left the negatives out and then I go, okay, this is my change. We know that there's a decrease in freezing point when we add solute. So if I started at negative 63.5, then I must be subtracting this, right? So I'm going to end up even lower. So my final freezing point is lower. So if you think about it, rather than saying, okay, it's final minus initial or whatever, because boiling point will go up, freezing point will drop. And that way you don't have to worry about pluses and minuses. So our answer ends up being, so our freezing point final is whatever, negative 65.6. A reminder, when you add and subtract, it is the place values. So that's why I only went one decimal place. All right, any questions? And also, just in case, for those of you who do like to watch online different places, everyone's gonna, some of them are gonna have a negative here, some of them are gonna have a negative in different places. And I think it's better to just think of it logically. All right, we're gonna do, does your answer make sense? That yes, we just said that when you add the solute, it interrupts the pattern. And so we see a lower freezing point. So our final freezing point was lower. All right, what we would have done in lab, similar idea that we have 0.186 grams of an unknown. So we'll just say question mark. Can't change that to moles because we don't know what it is. You're going to see these words. Can't believe they haven't shown up yet. So non-volatile, non-electrolyte. They are extra fluff words, but they're really important, and you know what they mean. So what does non-volatile mean?
Is it sticky?
Well, what does volatile mean?
It's resistance to flow.
So that was viscosity.
Ease of evaporation.
So if something's volatile, it evaporates really easily. This is something that is not volatile. So it means it does not evaporate. Non-electrolyte, an electrolyte means, so this non-volatile means does not evaporate. What that means is it's not going to contribute to the vapor pressure or the boiling point. And non-electrolyte means it's not an ion. All right. And then we put it into, I'm just writing my list here, 22 grams of camphor. This is our major, the 22 grams. Camphor is my solvent because I have more of it. So water is not in this one because I gave you two pieces. This is my solute. I don't know what it is. That's what we're going to figure out. And it tells us our new freezing point. So the freezing point of the solution or of once we mixed it was 176.7. So I wanted to also point this out. Freezing points are very different depending on the solvent. On this one, we were down at -60. And this one, our freezing points are like 176. So the nature of the solvent makes a big difference. The original freezing point, so the freezing point of just the solvent, which is known as the normal freezing point, meaning of the pure solvent, that was the 179.8. So the difference there is going to be your delta T. And then, of course, I gave you the K. So I'm going to pause. Actually, I'm not going to pause. I'm going to go ahead and crank through this one. All right. First thing you're always going to do, I'm just making a list to pull all the stuff out because I did not bring a highlighter out here. You can always highlight the pieces, but this is all the information we have. It is freezing point, so state your formula. So delta TF equals KF. And you can just write molality, or you can say moles of the solute, which is our unknown, over kilograms of the solvent. All right, we know delta T. It's the change between these two. So that's what, 3.1? So the difference between those, doesn't matter which way you go. I do this as absolute value again. I don't worry about pluses, minuses. That's going to equal my KF, which is the 40 degrees Celsius. My X moles, I don't know what that is. And I do know my kilograms is the 22.0 grams. Change it to kilograms. All right, does that make sense? We are solving for the moles. That's the piece we don't know. So rearrange, right? You'll divide by the 40, you'll multiply by the 22, divide by the 1,000. And while somebody's doing that, how many sig figs will we get when we punch that in?
Is it 2?
Only 2. That's one of the issues with this lab is the change in temperature is always really small and it limits your sig figs. And most students get really crappy data. So it is always an approximation. It's not like the titration lab that your teacher did really good on. All right, I wasn't going to press my luck. I got that this gives us, so my X moles comes out as 0.017 moles. Now, I keep the whole number in my calculator to go to the next step. But technically you only, I'm sorry, I lost the 0. And that was actually the point I was going to make, is just be careful because there's usually several zeros here. We are not done. The question wants us to find molar mass. What are the units of molar mass?
Grams per mole.
Grams per mole. So we want grams of our unknown over moles of our unknown. Right, so this is like step 1. This is my step 2. So I found the moles, 0.0017. That's going down here. How many grams do I have? Well, that was that first piece of information up here, that we have 0.186 grams of the unknown. So 0.186. That was given in the problem. And we divide 2 sig figs, it's going to come out around 110 grams per mole. So it's a rough approximation. It's not a precise art. And I'm grateful we're not doing this lab. The only fun part about doing this lab is it was the 7th week and you guys all got to know each other. And so everybody had fun just playing around in lab. And it was a really messy lab to clean up. All right, one more page. I was just going to keep going because we'll get done early then. And nobody has to stay after to do a worksheet. So osmosis. Again, there's so many great jokes and cartoons with this. Osmosis, what is it? Osmosis is a movement, right? And that's the whole idea of the cat. Osmosis is the solvent. It's all about the solvent. So the vapor pressure was all about the solvent was not escaping, or the freezing point was the solvent was not making a pattern. This is the solvent moving across a membrane. So we call it a semi-permeable membrane. Let's put it in quotes, semi-permeable. Our cell membranes are really elegant. I should I have a wall that needs a painting on it. I should do it of semi-permeable membrane. Reverse osmosis is when they make the solvent go the wrong way, but the solvent moves across the membrane. The solute does not move. So our cell membranes are barriers that keep the solvent, the water can go in and out moving across it. So it is the solvent moving. Students who've had biology, this ends up being a little bit tricky for them sometimes when we get down here and talk. It's more when you take anatomy and physiology because they get used to when there's channels. So if there's an opening like a door, anything can go in and out. That's a totally different game. This is assuming all the doors are closed. The solvent can still go in and out. All right, why you should care, again, are cell membranes. This is me, a biochemist, talking. And all right, so the formula, this is the classic formula. That is a pi. It's a capital pi. So it's a really big pi. So it can be whatever kind of pi you want. That M, this is where it drives us crazy. This M is moles per liter. That is not molar mass. The R is our 0.082057 and the T is temperature. So you can use this. I'm going to do it as PV equals nRT. And the reason I can do that is if I'm solving for P, which is osmotic pressure, I'm going to divide by the V, If I write the V just there, that is moles per liter. Oh, look at that. It's that formula. So I don't know why somebody had to write a special formula for this, but it does, for some reason, solutions do obey gas laws. So we're going to solve this. All right, so what is the osmotic pressure? Aqueous solution means that water is our solvent. It doesn't always tell you aqueous. There is no solvent given, so you assume it's water. And this is our solute. You guys remember R? It's in the good old days when you didn't have your notes, but this is the R we used that you just used on Tuesday. And what do you have to do to Celsius to solve this one?
Change to Kelvin.
You got to change it to Kelvin. So I'm going to pause, give you a moment to try it, see if you can get it. I can't remember how. All right, so 2.02 grams of urea. And I have that figured out. That's like around 1 mole is 60 grams. Then we multiply by R, just a reminder, 0.082057 ATM liters per mole. Okay, you can just write R, you can just write the symbol, but just to show you how the units will work out. My temperature, I do have to go to Kelvin. Gas laws only work in Kelvin, even for a solution. And you can divide the whole thing by volume, or so our 145 milliliters of our solution, and we change it to liters because R is liters. So 1,000 milliliters to a liter, or 1,000th of a liter is a milliliter. So milliliters cancel, grams cancel, moles cancel, K cancels, liters cancel, ATMs. Osmotic pressure is given as ATMs. It comes out as outrageous numbers. It's always like 5, 10. It's not the same as gas laws, even though we can use gas laws to solve it. So really, we didn't have to learn a new formula for that one. And so 5.58 ATMs. So when you add solute, does your answer make sense? We didn't have an original pressure to compare to, so when you add solute, the solvent is attracted to it. So the solvent moves to the side to where there is more solute. This is all about attractions. That's why we did all the IMFs. That's why we did, so the solute and solvent have a strong attraction, and so the solute pulls the solvent across the membrane. All right, you draw some cartoons, but on this one, does your answer make sense? We don't have an original number to compare it to because there is no osmosis if there's no solute to pull the solvents across the membrane. Reverse osmosis is the idea of them trying to purify water from the oceans and stuff. And so there's some actually really cool, innovative stuff with that. So the lab for next week is going to be another kitchen chemistry where you get to play in your kitchen, and then you do a lot of calculations. So the term iso, we've seen iso when we saw isomers and isotope. Whenever you see iso, it means same. I don't know if it's Greek or Latin. And tonic means salt or concentration. Not like you're thinking really hard and paying attention, but how much you have. So molality, molarity, percentage, mole fraction, those are measurements of concentrations. So why your teacher had to stay in school for a long, long, long time is how I draw a cell. It's a nice happy circle, and this is a happy cell. So cells, we're just going to make up a number. and say it's 0.9%. And if it's isotonic, outside is also 0.9%. That means it's the same. We have the same amount of solute inside and outside. So there is a flow of the solvent. My arrows are the solvent, but the flow in and out is equal. And my cell stays nice and chubby and happy, and we move on. Hypo means what? Hypo is low. So like when you have hypothermia, your body temperature dropped low. In this case, you have low salt. This is always on the outside. We're talking about the outside. So our cell is going, oh no. He is still 0.9, but now the outside is 0.1. It's low compared to our 0.9. Which way does the solvent move? The solvent is attracted to the solute. It's attracted to where the number is higher. So the solvent moves in. And so what happens to our cell is our cell ends up bloated. So it's like when you eat too much gluten or too much cheese that you get bloated, or it's a full moon and you just can't believe you ate the whole thing. He swells up. He doesn't feel swell, he's swollen. So the water poured in, trying to get the inside and the outside the same, and our cell gets bloated. All right, hyper is when you have high salt on the outside. And so when people are given IVs, they're given isotonic. That's actually really important. It's one of the big things that you get to learn about. So in this case, our cell, again, he's going, oh no, he's 0.9%, and on the outside, it's going to be 5%. So again, the water, the solvent is what moves, and the solvent moves to the higher percentage. So this time, the water moves out. So when you're a hypertonic, the water moves, it's going to move out, and you end up, he shrinks. There's a fancy name for this. It is called crenate. So not cremation, which is what they do when grandma dies, right? They cremate you, they burn the body. This is crenate, shrivels up. This is what a lot of you did as young. The boys usually do this. I found it really disgusting, but you took salt shakers and you do it to slugs, because slugs are a semi-permeable membrane. And if you put salt on a slug, you can watch it in front of you in just a few seconds shrivel up as the salt pulls all the water out. So Major, you didn't have slugs in Egypt. If you just take any salt shaker. So when I first
I
came
did
to
that actually
Oregon,
here, like 2 days ago.
I was horrified because I bought a house, I had slugs, and they were eating my pepper plants. Pimba was like freaking out because they ate all his pepper plants. And so I went to school and I was telling my students my woes, and they said, oh, just get salt. So I went out and I was like, okay, this is not going to work because this is really disgusting. Major liked it. All of you guys did this. And so I went back, we didn't have Google yet, right? And somebody said, oh, you get like a tuna fish can, eat the tuna fish or give it to the cat. Tonight was tuna noodle casserole. So all the animals are like, isn't it time to eat? Somebody gave us canned, like they went fishing and gave us real tuna. Not the same as the crappy stuff you buy in the store. But anyway, or you get a beer can and just dump out the beer. Or actually, no, you need the beer. So you put cheap beer into the bottom of the tuna fish container and you put it out in the middle of your garden. So I did that. It turns out it's a hypotonic solution. And slugs love beer more than they love anything else. They love cheap, like Coors Light or whatever's the cheapest thing there is. And I had a parade of slugs from all the neighbors. It was like 10 lines of slugs. I went out like a half hour later and they were just coming for the party. And I look in the can and there's all these like swollen, bloated, dead slugs. They were, I guess, in bliss. I don't know. But it was even more disgusting than the shriveled one. So now I have become one with the slugs. And, this year we have not had rain. So the slug issue is not as bad as it usually is. Which anybody who has a garden would agree. They are out there. I throw them over the fence. I'm a slug slinger. And that's like okay in Buddhism if you throw the slug because it survives. I send him a blessing as he flies on the wind. So I don't recommend any of those ways. I've tried every way to get rid of slugs. And in the Pacific Northwest, I don't know if you know, so snails, the banana slugs are true decomposters. They eat and they give like back to the soil. But the brown slugs, it was somebody was trying to make escargot. And so he imported these slugs and had a slug farm. And the slugs escaped because they're slugs and they can get through anything they need to. And yeah, they're just all over. Don't tell Joey, they probably end up in my smoothies because they're on the bottom of the chart and you didn't hear that either. Shanti doesn't care. I have yet to teach the mole how to eat the slugs, but all right. I think that's it. Any questions? Do the extra credit, do your lab. No office hours this weekend because there's no need for them. It's going to be a beautiful sunny day. Enjoy it. You can send me an email if you have questions. But anything you do will be fine. Just do the lab, get it done with, and good. That's it.